but I opted to do file reading because I wanted to go over that in more detail, and I want to take time to, again, go over the assignment a bit and do some file reading stuff. So rather than spending time on another in-class exercise, I think I'm going to just spend an extra day on file reading. And maybe start the in-class exercise that I typically have planned for next week. But we want to make sure, again, that we have plenty of time to go over file reading, because we spent a lot of time, not a bad thing, we just ended up spending a lot of time last session fixing some issues. So, what are we going to do about that? We are going to just, so a couple things to note. Let me pause this because I think, all right, so what we're going to do now is I'm going to just go over something that somebody mentioned I did last semester, right? I mentioned that that I had a mistake about latitude and longitude last time around with Hurricane Irma. So let's go ahead and just open up the Irma program for a bit. Okay, so I'm going to go to idle, and what we're going to do is we are going to go and open star files Irma, right? And we run this, and nothing happens because that's what we need at the moment, because we didn't tell it to do anything. Now, what we're going to do is I want to make sure you understand what I mean about moving the turtle, okay? Typically, if I were to do something like, so the way you want to move the turtle in this exercise is using the go-to operation to move your turtle to a specific XY coordinate. T.go-to, right? Given a X and a Y coordinate, we'll move that turtle to an X and a Y coordinate. In a typical Euclidean plane, typical starting point for our turtles, if I put in D00, this should move to the center of the screen. Let's go ahead and add a bit more to this program to make sure that this turtle does not just simply stop. Turtle.done, I believe, should do that. Yes, and now it doesn't disappear. And as you can see, our hurricane is nowhere to be seen because this does not use the Euclidean plane. This is using the coordinate system, right? This is using the latitude-longitude coordinate system. So let's go ahead and look up the latitude and longitude for Disney World. Okay? Disney World, latitude and longitude. So it is 38 north, it's 28.37 north and 81.57 west. Let's go ahead and take these coordinates. That gives us Walt Disney World. So if we move the turtle to these coordinates, we should be able to drop the turtle straight onto Walt Disney World, which that's very nice for that turtle. I mean, I'm sure that this turtle's going to be a hard worker, so he deserves that visit to Disney. So let's go ahead and copy this and paste it. There's the coordinates. So let's, instead of making him go to 0, 0, let's make this turtle go to Disney World. Okay. Now, let's go ahead and see. It is latitude 28 degrees and longitude 81 degrees. And if I plug that in, and I'll just plug this in right now, let's go ahead and just plug these in, and you'll see that we're running into a slight issue. 28 81, and turtle still doesn't show up. I don't get it. Why aren't we sending this turtle on a free trip to Disney? Does it not want to go? Well, maybe, but that just means the lines are shorter. But what's going on here? Well, look at what it is. It is latitude 28 north, 81 west. We say latitude, longitude, but that doesn't necessarily mean that's the order we should plug it in, right? Latitude are the horizontal lines going up and down. In other words, that's our y-coordinate. Why? Because it's north, right? It's north-south. So the 28.332 should go here because the latitude goes up and down. Whereas the longitude are the vertical lines. So we go there. So now if we flip them around, oh, does he still not show up? Where is he? Or did I? Oh, right. 81 is west, so that should be negative because west is negative, right? If we look at our coordinate plane, that should have it. And there we go. Straight to Disney World. Right? So GoTo moves it to that exact position. Negative 81. Why was it negative? Well, you won't have to worry about that in your file because in your file, it just gives you positive and negative numbers. No need to adjust and remember, oh, is this positive or negative? You just read that number in your file and you don't have to worry about that. But but in this case, right, 28.37, that's positive because north is up, so that's positive. South is down, so that's negative. Make sense? Here, east would be 81. West would be negative 81. So that's why we do that one. Again, we run it, and the GoTo makes it move there, right? If we told it then to move to another spot, like so, say maybe let's make it move up slightly to 29 degrees, okay? Same, then it will do so. So we can see it move across, and then it moves slightly up a degree. Let's go ahead and make it a bit more pronounced. 30, let's go with 35. Make it just slightly more pronounced, that movement up. Across, and then up. Right? So the GoTo just simply does it. It's very hard to see, but it is actually drawing a line. It's just, it's on a very dark, it's black on a very dark background, and it's very thin, so you can't really see it. It's right there. Hard to see, again, because it is just so thin. But that is how you move the turtle around. That's what I mean when I say that the latitude and longitude might be swapped. You got to remember which is latitude and which is longitude, which is x and which is y. Okay? Make sense to everybody? Okay. So, what else do I need to do here? Well, now that is covered, I'm going to go back to the file reading example that we had from yesterday and talk about how do we just parse a file, because what we did yesterday, on what we did on Tuesday, was, very straight, was just simply, can we read this file? So let's actually, work on reading this. So I had downloaded Treasure Island, okay? I downloaded Treasure Island, okay? But we hadn't really done anything with it, okay, other than print out the text. We've learned how to go, and we learned 3 methods, 3 techniques to read a file. They all start out the same way, which is important to know for the exam, because the second exam will have questions with file reading. One year the question was, here's a file with a list of days, like November 30th, December 1st, December 2nd, right? Here's the high temperatures in Philadelphia for that day. Here's the low temperatures in Philadelphia for the day. Find the highest high temperature, So questions like that. Given a file of temperatures, and that's formatted like this, find the highest high temperature. Okay, so those are questions I typically ask on the second exam. Okay, data is equal to, yes? Great question. I don't know. Typically, it won't be until you learn Monte Carlo approximations. It's typically in week 11. This is week 7. So Monte Carlo approximations will be the endpoint. Monte Carlo approximations are things that sound hard, but really the way all those are simply saying, man, statistics is hard. Let me not do statistics and instead just cheat and pretend I did them instead. It's a very nice way of doing things. It gets its name from basically figuring out the odds to games of chances in casinos by just being lazy and watching how many people win and lose, okay, rather than actually computing what the odds of cards being dealt are, because that's hard. Okay, so for most files, we just need this bit, okay, and because of this particular file, I had to add this encoding bit. You'll never need that in anything other than this example, okay. So for line in data, what are we going to do? So the three ways we learned how to do it: text.read, which takes the file and dumps the entire thing as a string into dumps the entire file as a string into a variable. The next way we learned to do it was read lines, which takes the entire file and puts it into a list of strings, where each item in the list is a line, right? So line 1 becomes index 0, line 2 becomes index 1, line 3 becomes index 2, and so on and so forth. It's an actual, so what do I mean by that? If I opened up, let's see, text files. If I open up pg120.txt, it's a Treasure Island. This is line 1, so that would be index 0. This is index 1, would be index 2, index 3, index 4, index 5, index 6, right? And so it would just simply store each of these in an index. And that's good because a lot of files, we want to go line by line to figure out what's in it. The third way of doing it, and this is the technique, by the way, that you'll want to use for the, most likely want to use for your Hurricane lab. The third way, which again I really like, is to use the for loop like this. Just simply say for each thing in our file, line in the file in this case, just do something with it. So what can we do with it? Well, we can find things out about the file. For instance, we could find out we could count the number of times the word silver appears in the file, right? Long John Silver is a famous character in Treasure Island. We can look at the number of times silver appears as a word in this program, right? What we do is, so let's take a look at that. So here what we've got is that we've opened up our so let's go review. I'm just leaving this here, but I'm going to pretend I'm doing from scratch. To open up a file, we do open, and then the file name. We make sure that the file's in the same location. When we work on our in-class exercise for this, with word frequency counts, that will be nice because it's built into Runestone. You don't have to worry about it. So open pg100.txt, and we open it into read mode, right? The file I want to read, and then opening it into read mode. For this particular, that's all I would normally need. For this particular file, if you're on Windows, you have to specify for this file, for some odd reason, that's a UTF-8 file. I don't know why I have to do that, but I just know that I have to. Okay? The next thing I have to do is read every line, because if I want to count how many times silver appears in this, typically what I want to do is line by line. I could technically just read it all at once and put it, yes? You don't have to do the range function? The what? No, because we're iterating over all the things in something. The for each loop says basically for each thing in collection. What the range does, range creates a collection of numbers for you to iterate over. So it creates all those numbers so if you say for range in 10, it's creating a range of numbers from 0 up to but not including 10 that it will iterate over. That's technically how it works, except that's a minor lie because that's how it worked in Python 2. In Python 3, it does what's called a generator instead, which is just a more efficient, which is more memory efficient way of doing that. But mentally, just think of it as creating a range of these numbers. Okay, so for each line in our data, what are we going to do? This reads that line, and what I want to do is I want to count how many times silver appears in this. So we'll do a running tally. Count is equal to 0, and then we'll say count plus equals line dot count, right, to count the number of times a string appears in here, silver. And then when I'm done, print count. Oftentimes a lot of times simply knowing your string methods will make your job a lot easier, right? And it says that silver appears only 11 times in the text. That seems odd. I know exactly why that is. This was deliberate. But why is it only counting silver 11 times in this text? If Long John Silver is a major character, his name is probably mentioned more than 11 times. Yes. Exactly. It's because it's lowercase over here. If I were to count uppercase silver, it comes out 215 times. Those are exclusive cases, right? Java, Python, C, C++, C#, Go, every single programming language is case sensitive. It cares about case. So how do I get around this? How do I deal with the fact that I want to count basically both the uppercase and the lowercase things, right? Because neither way I did it would include this particular spelling for silver, where it's all caps, which is what you would see if his name is in the table of contents for a chapter, right? So the way we do that is, well, the way I prefer to do that is when I'm working on my line, is I do this. For each line in the data, I would like that line, and I would like that line to be in lowercase. This is what I do. Line is equal to line dot lower. So I just simply take everything and convert it to lowercase. Lower turns everything into lowercase, right? Let's go ahead and just simply print that to kind of show you how it prints out and everything in lowercase. This is a terrible idea. I'm going to have to cancel it. But you can see how everything is now lowercase, right? Similarly, if you really want to shout at everything, you can convert it to uppercase, and now the entire book's shouting at us, right? Shouty case. These stories shocked our plain country people almost as much as the crimes he described. You know, it's amazing the amount of the amount of just projecting and making it loud that we do just because it's in a completely different case. There's no context that says I should be shouting that, but it feels like it should be shouted. All right. So what we do here is we do for line in data, line is equal to lower, and that converts it. Now, an interesting thing to know about strings. Strings are what we call immutable. Okay? What does that mean? We can't change them. We cannot change strings. So when I say this converts the string to lowercase, that's an oversimplification to help us understand. Instead, technically what we're doing, okay, is that we're technically taking the line, we're creating a new copy of it where everything has been converted to lowercase, and then we're storing it in the same variable. But, and the only reason I bring this up is that all that means is that we're not changing any of the lines in the file. We're not changing the original data that we stored this in. So that's kind of very useful that it's creating a new copy for us, essentially. But for all intents and purposes, this is just simply making it lowercase for us. Okay? And I'm more than happy if you do something like this. You know, create a new variable called lower line or something like that to do that. But there's no need to in this context, so we just simply basically replace what the variable is referencing. So we say line is equal to line.lower. We know that converts it to lowercase. And then we count the number of times silver appears. And that will be 227. We had like 11, 215, and then I suspect we had a few cases where it was all caps because it was in the table of contents. So 227 times that appears, right? Similarly with pirate, we can count the number of times that appears. Surprisingly, only 23 times in the book. But also there's because there's words like buccaneer, right? Or brigand. I'm not sure if they use brigand, but there's a lot of words that are synonyms for pirates. Yes?
What about sailor?
Sailor. Definitely sailor. Sailor. 21 times. So we've got a way of analyzing this text. We've got a way to kind of count the number of times something appears in this text, which is pretty useful. Now, a lot of the time on exams, you'll be working. Now, truthfully, when I give file reading on the exam, it's almost always reading a comma-separated value, like what you're doing in your homework for IRMA. Okay, it's almost always going to be a comma-separated value. Any questions on how to read files so far? Okay, before I continue on, I do want to give us a chance to just simply go and talk about the other bit, which is not as much as, which we don't really need to do so much, but it's the writing a file, okay? So let's go ahead and do, I'm going to create a new file called write example. Now this one's a bit easier because guess what? We do not need to download a file to do this one because we're going to be writing a file, right? But it follows a lot of the same syntax to start out with. The first thing we need to do is I'm going to change it up in my way. I'm going to say target is equal to open the file name that I want to write, okay, which is, let's call it output.txt. You can name it whatever you want, but I'm going to call it output.txt. And then rather than doing an R here for read, I do a W for write. Okay, read R for read, W for write, which, if you think about it, that's like, wow, that's kind of nasty to non-native English speakers because that W in front of write doesn't really make any sense, does it? Right? You don't hear a real difference between the first syllable of read and write, right? No difference between me going write, the command, and write for confirmation. Yes?
The W in front adds a slight pronunciation, like wrist.
It can. Wrist. Right. If it is, it's very subtle.
Maybe W read?
So W is, but anyway, W is for write. So this is all we need to do, and then to write something into a file, it's very similar to printing. What we do is we say the variable for what we're doing, target dot, let's see, write, and then here is some text. Okay? And then this last bit is we consider this impolite not to have this. And you should be technically do this on when you're reading a file, but it's fine. Most systems it's fine to leave this off. But this is the polite thing to do whenever you're done reading and writing a file, which is to say, I'm done with it, close it up. Okay, but it's important when you write because that tells the computer, no, we need you to don't have this in a queue anymore of operations you need to do. I need you to do it. I need to make sure you finish any operations that are pending. Okay, here's some text, and then I run it. Okay, now if I run it, save it, and then of course there's no output here because I wrote it to a file. So now I had this on my desktop. I created this file on my desktop. So wherever you created it, go into wherever you created it, okay? and you can look for it. And I've got a file here called output.txt. Okay, so what I'm going to do now is I'm going to go back into this. I'm going to go to File, Open, and again I'm going to select all files over here so I can see that. And output.txt, here's some text, right? Now, just to make sure just to confirm that I didn't have this already set up, what I'm going to do here is I'm going to do, here's some more text. And now I'm going to run it. And now I have to reload this. Go to recent file. Let's see. Am I able to read it and write it at the same time? I'm not sure. I don't know if I could change it. Yeah, here's some more text. So there you go. Now, write, what that will do is that it will overwrite anything that is already there. So if I modify this table, this text and say, and some more, right, I'm just direct and some more. More. Right, if I just do that, you can put whatever you want there. Right, just mash on the keyboard a little if you really need to take out your anger or something. Right, and if I close this and I run this, write file on it, it will go, okay, I want to create a new file here with this contents. And it will be like, oh, that file already exists? Oh, well, I guess it wasn't important. So generally you want to give your file, this a unique name. Generally you don't have to worry about overwriting anything you already have. But it does happen sometimes if you're sloppy about it. Fortunately, it's pretty difficult to be sloppy about writing files in this manner. But what if you're running like some data collection and you run a program and you want to add on what you have? Okay? You don't want to write a new file. We want to add on to this file. That's where our last command comes in. And write, I think I use write on the final exam, maybe? I think we use write on the final exam. Yes, we do. We use write on the final exam for the regular expression problem on the final exam. And that's an optional problem, if I recall correctly. So context, the way the final exam has worked for the past 3 semesters is that I give you 7 questions, you do 5 of them, 5 of your choice. One of them is on regular expressions, which is something you don't have homework for. It's just simply something I do a lecture for, and I introduce the topic, and if you decide to go and do that, then suddenly you have a very nice problem on the final exam to reward you with, as well as a very useful skill set. Regular expressions are one of those things that if you spend 2 hours learning it, it will repay in dividends for if you're doing any kind of programming work. Okay, so here's some text. So if I change this from write to some W to A for pending and run it, let's go ahead and close this file off, and I'll open recent files now. Here's some more text, here's some more text. And if I run it again, one more time, and let's run it one more time, right? If I do all those operations, guess what? So I've ran this 4 times total now. If I go to recent files, output text. And we see it's come out 4 times, although that's hard to tell. Why isn't it separated by new lines? Because I didn't tell it to separate by new lines. Unlike printing, where it assumes that you want to do a new line after every time you print, because that's nice and easy to read, writing is verbose. It does exactly what you mean it. Exactly what you say. So if you want new lines, we put them in ourselves. Target dot write, and then /n, And what we're going to do over here is I'm going to go ahead and change this to a, so I'm going to do this a couple times, right? Write to write a completely new file. And then A to add on to it, and add on to it one more time. And then we can also add on more and more to that. Target dot write you can put in as many write you need /n. So yep, there's no limit to the number of times you can call write. Okay. Instead, and so if we open up this recent file, we can see that all that output's in there. However, the one thing you cannot do is right after you close the file, because it's closed. This should fail. I'll be very surprised if it doesn't fail. Yep. Value error. I/O operation on a closed file. Right? And this just, and you close it because this makes sure that everything gets written to it so the computer knows you're done with it. Okay? Writing is not something you're going to be doing in any of the homeworks. I don't even know if you really don't do it on the exam, and if you did, I'd put it in that second page with all my extra notes, because it's not really that hard of an operation to do. But for completeness sake, it is what you want. This is what we do with it. So let's go ahead. So here's what we're going to do now. Rather than prattle on with an with trying to make up examples, we're going to start the exercise I have planned for Tuesday. Why? Just because I cut out the cryptography thing and I just don't see a space to put that in. We might revisit cryptography later in the semester, but I feel like making sure you have as many chances to interact with data like this, the file reading, will help you with this homework. So what we're going to do is go to Runestone, go to Foundations of Python Programming. You can find this either in, actually you wouldn't be able to find it in Module 8 because I haven't modified yet. So let me go to Module 8. Okay, and you can either directly click on it as soon as I've modified it right here, link options. And I'm sorry, this is just a busy time with the semester for me just because of everything that goes on during this period of time. So anyway, we've got this. So you can click on that there, or you can scroll down on Runestone all the way till we hit, believe it or not, part 11. We're skipping a few, and that's fine, because they're all very compact and do things that are relevant. And yeah, normally I'd go with substitution cipher, but I think this one, Monte Carlo simulations, really, not Monte Carlo, exploring common words in SETI, that's what I want to do and focus on because of, again, of file reading stuff. Okay? Okay. So languages are weird because they're man-made, and anything man-made is weird. Okay? We were kind of talking about that earlier with pronunciations of words. Okay? In many projects, like spell checkers, they require a long list of words. But there's things you can do like lexicographical analysis. You can figure out, hey, what things are important to languages. And the interesting thing about languages, all languages, is that all languages have words that are more useful than other words, more common than other words, that serve more functions than other words. Okay? So what we're going to do is that we're going to use a list of the 5,000 most common words in the English language. This list they say is based off of they analyze 450 million words from magazines, newspapers, works of fiction, and academic writing, although apparently whoever wrote this does not believe in the superiorness of the Oxford comma. So it is highly representative of the English language. The list we'll be using is made available by the Word Frequency Data Project. And the idea here is that this project counts the frequency of words. Right? What it does is that basically they have a bunch of documents, and then they have programs that read these documents and just simply count for each word how often that appears, and then add it to the grand tally. Yes.
So it says that there's a range of 1 to 60,000. Is that like their cap on how many words they have?
I think so. Quite possibly.
Are there more words than that?
Probably. Almost certainly. I mean, new words get added to to English basically every year. You know, a lot of them start out as parlance and then they get added. I mean, okay, for instance, was a deliberate misspelling of the term all correct. Yeah, and now it's just part of the normal English language. So languages are not static at all. And if you're a computer scientist, depending on how heavy you go into computer science theory, you might actually get really heavy into linguistics. We have an entire course called Computational Automata, which is all about basically describing computer languages as languages and mathematical languages and what they can do with that. Now, anyway, so it's a very interesting section for the title, which is what do common words in the search for extraterrestrial intelligence have? That's what SETI is. They listen to radio waves and try to detect if it's something that sounds like language. But if it's an alien language, how would we know it's language? And the answer is Zipf's law, Z-I-P-F, which is what we're going to be examining in this exercise. So basically put, it says that, as I mentioned earlier, words in languages are not evenly distributed. For instance, take the word the. The word the appears in the English language a whole lot. The word the has its own title, the article. And if you just listen to your sentences, you might be surprised how often the word the appears in your sentences. Okay? So the big operation of what we'll be doing over the next couple days is answering what are the 10 most commonly frequently used words, how does that frequency usage compare to the top 1 to the bottom 5,000, and what percentage of usage do those top 25 words represent in the English language? Okay, now that being said, humans are weird, right? You might be going, okay, you might be going into text and think, yeah, I'm going to read this text and I know that like E is the most common letter in the English alphabet. So in this text I'm reading right now, E is going to be the most common letter because this is an English book. And you'd be right, except for one case. If you were reading the book Gadsby, a novel which was written in 1939, you'd be incorrect about the frequency distribution of letters because it's a complete novel written without the letter E. Because they didn't have TV back then, or the internet, or social media, and this is how they had to amuse themselves. They're like, oh, if we didn't have TikTok or TV or something, you'd be learning time and spending time useful. No, you'd be producing weird things like this, which are definitely not useful. This is not useful. It's hilarious, though. It is hilarious. Just because we make assumptions about languages doesn't necessarily mean it's true for every document, but in general, these things are useful. So we are given this CSV file. And what's cool about this CSV file, before I even look at it, it says it's words5000.csv. What's cool about this in Runestone, okay, is that right now I don't have to work, just like how on a test, which is on paper, you don't have to worry about where that file is. It's somewhere in our imaginary computer that we're writing on the test, right? Similarly, you don't have to worry about where it is in the browser. It's perfectly fine. So we can just simply do open words.csv 5000 on this page and read mode. And I'll say data is equal to this, right? Before we even look at it, and I'll say print data, not data.read. We don't want to do that, but print data. And I'll run it, and it says, hey, I've got an open file in read mode called words 5000. It says, yeah, I was able to read that, no problem. I'm ready to do any operation you want on this, right? So the great thing about this is that we don't have to worry about downloading files and putting them into the right place. Isn't that great? So this just lets us get straight to the code. So let's take a look at what this file has, okay? So it's got rank. So at the top, in a lot of files, is a legend. Now, files may or may not have legends. Your IRMA files have legends on top of them. And what that does is just simply tell you what the columns are. So we've got rank, word, part of speech, frequency, and dispersion. All right, rank is fairly easy to understand. It is how frequency that word appears. The appears the most in the English language. Part of speech, A. You might think that's A is for adjective. No, J is for adjective apparently in their system. A is for article. That's the role that the fills. It's an article. It's the article. Rank, the, word, be, that's a verb. Have, the, verb. Next is the frequency. That is the number of times they have counted that word occurring. So for the word a, right, which is an article, that appeared, that appeared in the documents they were counting 10,144,200 times. The last one is called dispersion, which is basically in what percentages of files does this occur? How frequently across files this occurs? So 1 means that this is the most evenly distributed thing across all text, where 0 means this does not really, it's a score from 1 to 0. 1 means it appears a whole lot in everything. 0 means it appears primarily in really rare specific stuff, right? So an example they have is the word re, which occurs 15,000 times, but its dispersion is 0.47 because you don't use re in regular text. You use it if you're doing legal writing, right? You're doing it if you're writing legal documents. Okay? So similarly, medical terms might only really occur in medical documentation, right? Right? For instance, I cannot remember, but like for instance, if in medicine, if you're displaying signs of vomiting, they have a specific medical term for that is not vomiting. They use a completely different term. And I read it once and I'm like, what is that term? Oh, that's what it is. So words, again, kind of can live on their own island. For instance, the word fracas, meaning a kind of fight, that only exists in newspapers. Like only newspaper journalists will use the word fracas. Okay, so there's kind of words that exist as islands there. That's what dispersion is. All right, so we've got these words. We've got rank, word, part of speech, frequency, and distribution. Okay, and this box does have the entirety of everything, and it's got its own drop down. And let's go scroll down, and all the way down we see apology and till. apology here being a noun, which is a shame because really there should be more apologies. Maybe things would be better if we learned to apologize a bit more. Middle class, kid, plaintiff, kid here being a verb. So they distinguish kid being a verb, I kid you not, versus kid being a child, or kid a goat. Which is the last one being, of course, the superior usage of the word kid. So the first thing we want to do is read the file and store the contents into 5 lists. Remember, as you read each line of the file, the line will be represented as a string. Your goal is to take the line and split it into 5 parts and put each of those parts into the appropriate list. So what does that mean? Well, I'd like to have a list of words, and I'd have to have like 5 lists. One for the rank, one for the, so let's see, sorry, give me 1 second. One for the rank, one for the word, one for the part of speech, one for its frequency count, and one for its dispersion. So, and that would mean, so the would be at rank 0 in word, it would have, and the rank and at index 0 in rank it would be 1, and dispersion would be, and dispersion's index 0 would be 0.98, and so on and so forth. So let's just go ahead and kind of show this, right? So let's first, but before we can start analyzing individual fields, we need to make sure we can iterate over the file. So for line in data. Now we're actually going to have to rewrite this a few times. Print line. Run it. And we're able to read this just fine. We read all the lines just fine. We printed it out to confirm that was the case, and it worked just fine. Okay, the next thing I need to do is that if I want to work with the individual fields in this file, right, what do I need to do? I need to get each individual field. The easiest way to do that with comma-separated values is to separate them by commas. Right? Make sense? I want to take each line, for instance here, just 66, it's right now just one big fat string, right? It's very hard to pull the data out of that because the words are different length, the number of things are the number of times it occurs is a different length. So instead of just trying to read a string, what I'm going to do is I'm going to take this string and split it up. Line is equal to line dot split, comma. This is probably the most important step in here. And then we're going to print that line out again. So again, the split takes a list and takes a string and turns it into a list of strings. As seen when we do this. Print line. So there we've got our list over here. 5A, this many times, and this dispersion. So that's great. Make sense? So split allows us to access these all individually. What do I mean by that? I can print out I can print out each index. So if I don't have this, actually I'll show you. Print out line 0 and line 1. If I do this, okay, I'll print out the rank and the word, 1, the, 2b, 3, and 4 of. So I'll print those out. But if I don't split it up, then this means the character at index 0 and the character at index 1 because it's still a string. Make sense? So what does that mean? It means when I run it, I get RA 1, 2, 3, 4, 5, and then just this, because it just prints out the first 2 characters. When I do this, though, I split it up into fields, which is really nice. Okay? In fact, you might want to rename this variable as fields over here, stored in different things, but that's fine. Okay? Now that I've got this, we do have a bit of an issue, though. What is that issue? I still got the legend on top. And I still have this legend here. That's could be a problem and it might not be a problem. Okay? Right? So we'll ignore this for now. but we'll have to keep that in mind, right? It will become an issue in just a bit. So like, if I want to make and so how do I do, so what's the objective? I want to take this, after I split it up, I want to take each part of the data and store it in a list. Okay, so how do I add all those words to a list? Well, I'm going to create something called words is equal to an empty list. And what I do is, to add a word to that list, I'll just simply go words dot add. I believe it's dot add. No, it's append in Java. Sorry, it's append in Python. Words dot append line 1. Print words at the end, because otherwise you'll be repeating. And there we go. So what I want you to do now is create the other 5 fields: rank, rank, dispersion, participle part of speech, and frequency. And actually, let's line this up even better by calling this one just word. That way we can keep them all to 4 letters, like rank, freak. So, and try building all 5 of those so that you have those 5 separate data fields. Okay, I'll give you a few minutes to do that. Thanks for bearing with me on this. I know I've been droning on a lot, so it's not as interesting as the previous lectures. But again, I want to make sure that these are things that we really are able to nail down here. So on line 7, it's in inside, which means that it's in the step. We're seeing that, so we can't see that outside the folder. No worries. I'm going to do this right now, in fact. All right. So let's go ahead and add build our other lists. Undefined words, it says. Fine, okay. So what we're going to do is we're going to create all the other lists. We've got rank. We've got the word. We've got the frequency, which is, sorry, we've got the part of speech, so that's part. We've got the frequency, which is the number of times it appears. And then we've got the dispersion, which is that how broadly, how specialized is this word? With the high score being unspecialized and the low score being very specialized, very niche. Right? So we've split this line up into multiple fields. And so we can say rank is equal, so we can do rank dot append line 0 because we know that the rank is the first part of this. And then it's just a matter of doing copy paste on the rest. The part of speech is the second part. Sorry, part of speech is the third thing, so that's index 2. 3, 4. Then we had frequency. I'm just working off of memory. That's how I know it. I just looked at it. I'm working off of memory. Make sense? 0, 1, 2, 3, 4. Right there. So, and because if we look at the top of this file, Gesundheit. Right. Rank, word, part of speech, frequency, dispersion. That's why I'm doing it in that order, right? And then I just simply did the first 4 letters of each of those because 4-letter words are just so expressive. So, what we've got here, also it just lines up and that's really nice and organized and clean looking. So we've got this. Let's go ahead and just print out frequency over here, the frequency, and we see that we print out frequency, so we see over here frequency 220 million, and then the next rank, and the next value, and the next value, and the next value. Okay, frequency over here, though, look at that. That's not a number, and we're including it in our numbers, essentially. We've included the legend in our numbers, which is a bit of a pain because these are numbers, and I have them stored as strings, and if I want to convert them into integers, which is what they are, like this, I'll get an error. It will tell me, error. You can't convert frequency into a number. Similarly, if I try to convert this into a float, I'll have some issues here too. And if I try to convert this rank into an integer, because the rank is an integer, I'll also have issues. So what do I do? This is the problem you have on your on the IRMA file, by the way, where that's at the top. Well, so the issue is that I need to skip that first line somehow. Okay. Now, when I read over the file like this, I don't really have much control. When I say, here's open the data, and I've got this, right? I don't really have much control over that. I have to go over every line if I use a for loop like this. If I want more control, I have to actually store the contents of a file in a variable. So that's exactly what we're going to do. We're going to say lines over here is equal to data dot read lines. Now you may like this or you may absolutely hate me. This is just my preference. Okay? And you may absolutely hate my preference that I just created a variable called lines and I have a variable called line. Right? I have a plural and I have a singular. Because I like to write like this. For line in lines. But it also looks kind of horrible because but it makes sense. It's for the singular thing in the collection of those singular things, which is a plural, right? If you really don't like that, here's my suggestion to you: for L in lines instead, and replace line with L, and it gets the same idea across. It just by being a single letter, it's now really emphasizing that is the singular in the plural. And so you get the same kind of idea, just displayed in a different way, and that can be really nice. What's the correct answer? Whatever makes the most sense to you. What makes it easiest to read for you. Okay? But don't do something nonsensical. Don't do for X in L. or something like that. Because then when you come back because when you come back to this a week later, you'll be like, who was that person last week who was coding for me? Because that person was a madman. That person was insane. That person was, I don't know what they were thinking. It's always worth the effort to put in these kind of things. So now that we said this, for line and lines, right, I'm still going to have the same issue, right? But now the idea here is that now, because I have a bunch of lines, this is a list, right? This is a list of lines, a list of strings. It's a list, I can do list operations on it. Specifically what I can do is I can do this. I can do a slice. Now you can do this either here, or, if you prefer, and I think actually for readability's sake, this might be more preferable to do this over here. Lines is equal to lines 1 slice notation. What does this do? This says I'd like all the things in lines starting from index 0. Sorry, from index 1. Skip out index 0, please. I don't want index 0. Make sense? We don't need index 0. Index 0 here is not something we need. And now when we run this, we print the frequency, we print the word, right? We're not going to be seeing that legend anymore because we basically sliced off the line that had that, which was the first line. So you want to do something like that for your hurricane tracker assignment. Yes?
In the dispersion part, there's like a /n.
A /n at the what?
For the last one.
Like if you print out dispersion?
Yeah.
Does it give you an error?
I'm just thinking the error. It's just like, after, okay, well, mine is messed up.
I converted mine to a float, so.
Okay, that's probably why.
Yeah, if you convert it to a float, it should get rid of the, but the reason you were seeing, so the reason you see that /n, and let me go ahead and show you what you're seeing. Let me show you what you are seeing so everybody else can see it and have context. You're seeing this, right? This is because the dispersion is the last thing in the line. So it comes with to go on to the next line, it has the new line character. So when you do the read lines operation, it stores that new line character. It stores that new line character. And because you split it up, and this is the way lists present things, it's just not rendering it as a new line because that would break the readability of the list. So it displays it as a physical new line character, like that. So it says, yeah, it's the last thing in the line. We know that because we saw a new line character here. Here's the new line character. I don't know if you want to do anything with it or not. We don't, so we don't. And so the nice thing about these int and float operations is that if you've got this white space characters around it, be it tabs or spaces or new lines, it'll say, yeah, it's white space. We know how to handle white space. We just get rid of it when we convert. All right. So as a bonus, we've got this little XKCD comic here, and we're going to have a few of those in here. Languages change over time. So here's the frequency of the word sustainable in the English text as a percentage of all words by year. So graphing it out, and we see this is a log scale graph. So we see basically it's percentages of percentages over here for its usage. Present day, the word sustainable is approximately, somewhere between 1/100 of a percent and 1,000th of a percent of all the uses of the English language. But it's on a log scale over here, and we can, extrapolate from that. So average in 2036, sustainable will occur on average once per page, and if we extrapolate further to 2061, sustainable occurs on average once per sentence. And by 2109, all sentences will just simply be the word sustainable repeated over and over and over again by just simply extrapolating that data. with the conclusion, the word sustainable is unsustainable. So when we get back, what we're going to do is we are going to, on Tuesday, we will examine something called this phenomena of Zipf's law, which we'll see basically is that something, it's the reason and we're going to learn more about what I mean by when we say that I use log scale, that the graphs are in log scale. Science tip, log scales are for quitters who can't find enough paper to make their point properly. Log scales are when we change the y-axis of the graph to be, instead of to be equal to the same kind of spacing as the x-axis, it instead turns the y-axis into an exponential spacing, or logarithmic spacing, but everything is basically, every point is an increasing exponent. So, because otherwise this becomes ridiculously hard to kind of, to make the point, to graph. We'll be seeing that next time. We do see logarithmic scales in real life. We see that most noticeably in if you live in an earthquake-prone area, you'll see that in the Richter scale, where a difference between a magnitude 4 and a magnitude 8 is not the earthquake is twice as strong, or better yet, the difference between a magnitude 2 quake and a magnitude 4 quake does not mean it's twice as strong. It means that the earthquake is 100 times as strong, because each of those numbers represents going up by a power of 10. So that's what you see in logarithmic scales. Okay. All right, with that, I think we've reached a great stopping point, so I'm going to go ahead and stop recording.